Hi everyone, I'm Shuqi from Carnegie Mellon University, and I'm so glad to introduce our paper, Automatic Analysis and Influence of Hierarchical Structure on Melody, Rhythm, and Harmony in Popular Music. As we all know, structure is one of the most important elements in music, ranging from low-level melody and rhythm motifs to higher-level phrases and sections, especially in recent music generation and evaluation tasks. How is music influenced by different levels of structure? And how do we determine the hierarchical music structure? These two problems became more and more critical in today's AI music creativity. Although there is a great deal of work relating to music structure, and we reference some of them in the paper, however, these two problems are still not well formalized. For example, there are many structure segmentation and analysis papers, but seldom do they study how music is influenced or structure hierarchy. Therefore, the goal of our paper is to tackle these two problems using the data-driven approach. Let's look at the first problem. We found two levels of structure in our analysis of popular music, composed of sections and phrases. For example, in this song, there might be multiple repetition phrases, like AABBB here, and each phrase usually contains 4 to 16 bars. And by combining those phrases, we can have bigger sections that forms the whole song. For example, in this song, there is an intro, a verse, a transition followed by a chorus, and the outro section. Very typical pop song structure. So the question is, do these two levels of structure really exist? Are they just larger groupings? We hypothesize that there are different systematic effects of different structure levels that are visible through melody, rhythm, and harmony. If the hypothesis is true, then these two levels really exist and are important for music composition and perception. We test this hierarchy on a pop song dataset that contains 909 Chinese pop songs in MIDI. Notice that these MIDI files have separated melody and accompaniment tracks. We first determine the two-level hierarchical structure through an algorithm purely based on repetition and similarity detection, which we will talk about it later. And then we analyze the structural influence. Now let's look at some data. First, this is a figure showing how harmony interplays with different levels of structure in major mode. This figure has two axes. Vertical axis represents probabilities, but the horizontal axis is not time. It represents different locations in a song. For example, background means all the locations, no specifications. And next is the start location of a phrase, start location of a section, and so on. Here, different colors are different chords. Now let's assume if structure has nothing to do with harmony distribution, then all of the lines will be flat. No difference, right? And if there is only one level of structure, say we only had the big section structure, then the smaller phrase start, phrase middle, and end locations would be all the same, that's similar to the background. But it's not. Similarly, if the only structure was the smaller phrases, then when you get to the end of a section, that would be the same as the end of a phrase. But that doesn't hold either. For example, 5 chords, which is a purple line, are more likely to see at the phrase end within a section, but not at the real end of a section. Next, Let's look at melody pitch scale degrees instead of harmony. Since melodic pitches are strongly influenced by chords, we would immediately expect to see that melody depends on structure. So here, we count only melody over tonic chords. Similar to previous harmony figure, if pitch distribution is independent of structure, all lines should be flat. And if we only have one level of structure, there shouldn't be difference between phrase and section locations. For example, we can see that scale degree 1 in melody, the blue line, tends to occur at the end of sections, but not at the start or middle of phrases. Similar things happen with rhythm, chord transitions, and other music elements, and you can read more details in our paper. Okay, so far, from the data analysis, we observe that there are at least 2 levels of hierarchy, and we discovered 2 of them, phrases and sections. And also, we see systematic influences by 2 levels of structure on melody, harmony, and rhythm. Here are more facts about our structures. For over 90% of the songs, 50 to 95% of their phrases are melodic phrases, which contains clear vocal line melody. And most of them are 4 bars or 8 bars long. There are typically 2 or 3 sections in a song, 3 or 4 phrases in each section, 1 to 3 distinct melodic phrases in each section. And data further shows that 20% of the sections are exact repetitions of the previous section in terms of phrases. For example, the first section is AB and the next one is also in the form of AB. While 29% of the successive sections repeat a suffix of the previous section. For example, AAB and the next section is AB. And 18% repeat a prefix. After studying the influence, let's look at how do we determine the hierarchical music structure. We propose a novel algorithm purely based on repetition and similarity. Why is this important? Imagine, if the structure are determined by tonic, then all the previous influence analysis are not making sense anymore. Thus, it is critical that we do not encode any domain knowledge in the structure segmentation, only depend on repetition and similarity. Here comes the framework of our structure analysis algorithm. First, we did some pre-processing steps of the MIDI. We extract the chord labels from MIDI and quantize them into beats, and also quantize the melody to 16th notes. And then, we design a bunch of similarity metrics to detect repetitions, and use a novel A-star heuristic search algorithm with dynamic programming to come out with the phrase-level segmentation. In the last step, we propose some simple rule-based methods to further analyze the section from phrase-level results. Next, we will briefly introduce the representation of the structure hierarchy. How can we evaluate the structure, design of similarity metrics, algorithm procedure, and experiment results. This is a representation of our 2-level structure. Each letter represents a phrase, followed by a number indicates the phrase length. Same letter means repetition. Uppercase letters are melodic phrases that has clear vocal line melody, while lowercase means non-melodic phrases, usually intro or transitions. Notice here group of bold phrases separated by empty space is section. Furthermore, for non-repeated measures, we use letter X to represent them. Next problem is how do we evaluate a phrase level structure? Is it the optimal or not? There is much ambiguity here. For example, suppose we want to analyze sequence of 8 measures. Use U and V to represent these measures, and we can describe the repetition as A4A4, where A is UUVV, or A2B2, A2B2, where A is UU, B is VV. Or we can even do A8, where A is the entire piece. But some descriptions are simpler than others. If we just count characters, we can see the first description is the shortest. So we formalize this idea as the structure description length, which is a weighted sum of number of segments and how much it takes to describe each segment. We believe that the structure with the lowest SDL is the most reasonable one. We look at every possible structure segment and pick up the one with the lowest SDL. Thus, we need a way to determine whether two segments are actually repetitions. This is how we calculate similarity between two sequences of measures. We form a weighted sum of the three different attributes. They are melody contour similarity using dynamic time warping algorithm, chord-tone similarity matrix, and rhythm onset similarity comparison. And if the weighted sum exceeds the threshold, we then consider the two segments as a repetition. Detailed algorithm steps are designed as follows. We first find all repetition phrase pairs using the similarity matrix on previous slides. For example, segment from measure 1 to 4 is a repetition of measure 5 to 8. Then we merge these repetition pairs into sets that contain multiple repetition phrases. For example, here, these three repeated phrases form a repetition set. Next, we find the best combination of repetition sets that achieve the lowest SDL score using A-star search and dynamic programming. We further adjust the phrase boundaries. For example, 4 measures of phrase A followed by 1 extra measure can be merged into 5 measures of A if passing the similarity threshold. Finally, we use the non-melodic phrases and remaining non-repeated measures to detect section boundaries. Further optimizations and approximations are also possible. You can see details in our paper and appendix. Experiment results show that our full algorithm achieves 92% accuracy compared to human label, and its average runtime on a personal laptop is only 21 seconds for 80% of the songs. In conclusion, we propose a novel algorithm to extract repetition structure at both phrase and section levels from MIDI dataset, based on repetition and similarity. And we also discovered that melody, harmony, and rhythm are all organized to reflect different levels of hierarchy. In the future, we hope to explore lower-level motifs and patterns rather than just higher-level repetitions. We can use this work to generate more coherent music, especially pop music, and evaluate music structure in AI music generation. Also, since results of this work are closely tied to established music theory, it offers a data-driven approach to study topics in music theory, such as chord function and melody. Thank you so much for your listening. Any questions or comments?